What's up people, this is Milosh. Welcome back to my channel. In today's tutorial, I want to show you how you can create effective temperature anomaly maps for the entire globe using both Robinson and the orthographic projections. Let's kick off our adventure by first of all installing and then loading the package that we need. For that purpose, we need the Pacman package. So unless you already have it, you should install it using install packages from base R. Now that you have the Pacman package, this package is going to help you install and then load the packages that you need using simply this p_load function. And then over here, we'll provide then the names of the package that we need. The first one that we will need is the rutils package, which we will use for unzipping a gunzip file. The second one that we will need is the Terra package for working with raster files. Then in order for us to fetch the world shapefile, we'll be using the jsco_r package. And then for working with shapefiles, we'll be using the SF package. Now, in order for us to create a good legend, we also need to create legend breaks. And for that purpose, we will be using the class int package, which helps us create breaks based on natural intervals. Now, for plotting itself, we'll be using ggplot2 package, which comes within the tidyverse umbrella package. For plotting raster files in Terra format with ggplot2, we will be using a very cool tidyterra package. And then last but not least, we will be also creating here a binned breaks for our legend. And for that purpose, we can utilize the color space package in R. And to sum up, these are the packages and their versions that I will be using in today's tutorial. Our next step is to query the temperature anomaly data, and now we'll go to the NASA website where I will show you how you can do that. The temperature anomaly dataset comes from NASA Goddard Institute for Space Studies, which is available at data.giss.nasa.gov, and over here you will find multiple datasets and images, but we are interested specifically in the temperature one, and the first one, which is called GIS temp or GIS surface temperature analysis. So if you click on this one, it's going to take you to the main page where you can find main information about these datasets, as well as news and updates, contacts, citation, and also some background history and updates. Finally, at the end of this page, you will find also a few datasets. For our purposes specifically, we will be using in today's tutorial these gridded monthly temperature anomaly data. As you can see here, there's some information about them. So these are 2 by 2 degree grids, and they're of course in different ways here. So these are net CDF files, but they're all compressed. We'll be using the first one, which is a land ocean temperature index at a very high smoothing. And this one actually covers, as the name says, both the land and the water bodies. Now, if you want to read more about this dataset, you can also navigate here to the bottom of the page where you can find this readme.txt file. And then if you click on this one, you will find then more about it. For now, what we're going to do is we're going to navigate back to this land ocean temperature index. This first one that I just highlighted, and then we're going to copy this link and go back to R, from where we will actually fetch this data locally. All right, and we are back in R, and over here I pasted the link to the data. One thing about this data set before we move on. So this is the temperature anomaly in Celsius for the average temperature in the 30-year period between 1950 and 1980. All right, so the first thing we want to do here is we want to turn this into a string, and then we want to assign it to an object which we're going to call URL. And then from base R, we'll be using download file and passing here this URL link or URL. Then the second thing here is that we would like to have also the destination file. So for the destination file, what we can do here is use from base R this function base name, and then pass this URL, which is actually gonna then fetch this part. So basically the name of the file itself. And then we can pass it also here. And then the very last thing here is to use the binary mode for downloading this file. Downloading this file is very straightforward. It's a very small file, but what we got is the gunzipped. And this is where rutils come in handy. So over here, we'll be using rutils to then unpack this compressed file. So from our utils, we can use a function which is called gunzip, and we simply just need to pass here this dest file name. Once you do this, you will be able to then load, of course, this file. And for loading, what we can do here is we can simply use then Terra Rust. So I'm actually going to call this temp anomaly. And then I'm going to use here Terra Rust. And then for Terra Rust, what we want to pass here is we want to pass the file name, but with a different extension. So we'll be using here gsub to get rid of this old extension and give it a new one. Now, in our file name, if you actually go here and see, we do have this nc or netcdf file name. So we just need to get rid of this .gz. So .gz needs to go away. So over here, we write this is the first parameter that we want to get rid of. The second one is what we want to return, basically the empty for that one, for the replacement. And then the file or the name on which we want to apply this is destination file. Now, if we spec this raster file, what you will see here is the dimensions. So this is for the entire world. This is 2 by 2 degree. And we are talking here about the WGS 84 coordinates reference system. Now, one thing you might be confused here is the unit. So the unit here is not Kelvins, it is Celsius. And you can go ahead and check also the README file for the specific data set. There are, of course, these very weird names, but there's fortunately also dates here. So as you can see here, the year level, or actually the month level here, is denoted by the 15th day of that month, followed then by the month number, and then finally the year number. So you can see this data set goes all the way from 1880 January to April of 2024. So what we'll be doing in this tutorial is first of all checking what is the anomaly for the month of April, and then I'll also show you how you can also calculate and map the anomaly for the entire year. All right, we have the temperature anomaly data. Now we're going to fetch the world shapefile using gsco-r, and I'm going to call it simply world sf. And then from gsco-r, as always, we'll be using gsco get countries. Now we need the entire world, so we don't need to specify either regions or the countries, but I would like this one to be actually lines and not polygons, because lines are very easy to then use for turning into different projections. In this part, I will show you how you can subset only the data for a specific month. And in this case, we'll be using the data for the last available month, which is April. So let's go ahead and create here a new object, which we are going to call temp anomaly April 2024. And then over here, the easiest way to actually filter the data that we need just for April is to use subset function from Terra. So we're going to be subsetting here our main object, which is temp anomaly. And then here, the way to subset is to use time from Terra. So time, and fortunately, we do have time recording there. So we're going to, again, here call temp anomaly. And then within this one, what we want to do is we're going to subset only the April raster file. So that means the following. We need to here, first of all, coerce that string object signifying time into date. And then we need to specify that we want April 2024. So that means 2024-04. And then if you remember 15, which signifies actually the day, the generic date for every month. Now, once you have that, we can also quickly check if we really managed to filter only April. And you can clearly see here, we have the data for April 2024. Okay, that's fine. Now, what we can do also is create some very, very simple map here using Terra plots. So we can actually plot this newly created, newly filtered object for April 2024. And then next to this, what we can do is we can also add here that shapefile of the world, so which is called world_sf. And over here, we simply need to put that we also want to add this element. And then once you actually run this, you should be able to see the following graph. You should be able to see this map of the world with temperature anomalies ranging from minus, I would say, 5 or something to 6, and you can also see there is some kind of a missing data, especially around Antarctica. Of course, this one utilizes just the simple WGS84, but I will show you in this tutorial how you can convert this into the Robinson projection, which is mostly used for creating temperature maps. And to reproject to the Robinson projection, we need to actually pass this string to this object Robinson proj, and then we can use Terra project to reproject a raster file into the Robinson projection. So let's actually do that by creating a new one, which we will simply call the same way, but we just add here proj so that we know what's going on. And then from Terra, call Terra project, and then pass, of course, this previous one, temp anomaly 2024, and simply say here that we want to reproject this into the Robinson projection. All right, so once you actually run this, you can then inspect whether we really did that. So you can just run this again, and you can actually see here that the new coordinates reference system indeed is the one that we designed. And you can also here see that in terms of the extent, we now have different coordinates compared to the WGS84. All right, now once we are done with this, what we also need to do is we need to reproject that world shapefile. All right, and then we can also create some simple plots so that you can visualize and quickly see whether you really made it. All right, so to do that, what we can do is create a new object, world asset proj, and then we can use from the asset package this st transform option. And then what we can do next is simply pass this world sf. And then as the second argument, you need to specify what is a CRS. So in our case, it's simply Robinson proj. Now we can go ahead and simply visualize this and check whether we indeed achieved what we planned to achieve. So again, we can use here Terra plots. Now we can pass this newly created raster file to it. And then in the second phase, what we can do is also plot this world sf proj and put it also here. And of course, just specify here that we'll be adding this plot. And then once we run this, you will be able to see the next map. And we have the map with the Robinson projection. As you can see, we successfully managed to transform both the shapefile and the raster file. Now, in the next step, we will utilize the power of ggplot2 to, of course, change the colors and add some more details to this. And of course, also change the legend breaks. Okay, but before we jump into ggplot2, I also want to show you how you can create an ellipsoid, which is so often presented in these temperature maps. So this is how we can do that. First of all, we're going to create world BB. This is how I'm going to call it. And then what we're going to do here is, first of all, we're going to get rid of these national boundaries. So that's the first thing. The second thing, what we will do within this, so is a nested function, we're going to create actually a grid here. So we're going to use st make grid from the sf package. All right. So, and then when we actually do that, the very last step is to create another nested function, which is we're going to building this on top of the bounding box for our object. And the object is world sf. And over here, the very last step is we need to specify, okay, how many parts this grid is going to have. So we are going to make it just simply 100. If you want a smoother one, you can of course increase this number. And then the very last step, and a very important one, is that we transform this. So we need to transform into the Robinson projection so that we can actually then plot this together with our world shapefile and also the temperature anomaly raster. All right, and now if we want to visualize all the three elements together, what I'm going to do is I'm just going to use this line of the code that we previously had. I'm going to put it here, and then I'm just going to clone or copy this last line here, and then replace here this with this world BB, and then just run this code. And we successfully added the ellipsoid to our map. But if you zoom in around the poles, you will notice that the raster file actually goes beyond this ellipsoid limits. So what we want to do next is we want to actually crop our raster file and then make sure that the raster file falls within the limits of the ellipsoid. for redoing the ellipsoid or the raster actually, so it fits within the ellipsoid boundaries, we'll be using Terra crop. Now for this one, I will not be creating a new object. I will simply be updating this temp anomaly April 2024 proj. So here calling crop from Terra and then passing this object over here. And then finally, what I also want to do here is you need to provide a mask that you want to use for cropping this. And of course, this is going to be the ellipsoid object. All right, so now once we actually rerun this, you should be able to see a modified map. And on this map, you will notice that what we managed to do is around the poles that we managed to get rid of course of this extra space. And now our raster file completely falls within the boundaries of the ellipsoid. As we're getting ready to create our map with the help of ggplot2, let's first of all do some prior steps. One of them is to create legend breaks. The second one is to define our color palette. And the final one is to create a theme for our ggplot. So let's start off with defining breaks. For breaks, we'll be using natural intervals. So here we call to rescue this class int package, which has a function which is called class intervals. Now within this one, we first of all need to pass the values, but we have a raster file. So how do we do that? Luckily for us, Terra has a function here, which is called Terra values, which is going to extract these values for us. The only thing we need to do here is to provide the name of the raster file. The second one is to define the number of breaks. So what I'm going to do here, I'm going to define 8. A good thing is to define actually the odd number of breaks since we want 0 to be the middle one. But I tried actually doing breaks here and it always gives me 8. So no matter what I put, so this is the best one. The reason why it gives me 8 is that because for the style, I'm going to be using pretty breaks. And the pretty breaks are the ones that you also saw while we were using or creating those sample maps at the beginning. So we're going to go for this one. And then the final thing, in order for us to fetch the breaks from the list here, we also need to specify this argument here. All right, now that we're done with this, we're going to dive into the HCL colors and we're going to use one of the palettes that they're using, which is called temps. It's specifically designed for temperature and for these very high values, which are denoted with warm colors. It doesn't use a red, which you usually see. Red is a very aggressive color and I try to avoid it. So I chose temps here because it's using pink instead, and pink has a bit of a milder tones compared to red. So I'm going to deviate here from the standard maps that are used in the field where they use blue and red. I find them very, very divergent, and also I find red, again, saying very aggressive in this context. So let's go ahead and define here calls, and then let's call HCL colors from base R. And then again, let's base actually the number of the colors we need on the length of the breaks, meaning that the number of the break elements here will define also the number of the colors in the palette we have. And then over here, what you also need to do is then define the palettes. If you're not happy with the temps one, you can also check the website with other HCL divergent colors, so you can also do that. I will leave the link in the description box below. All right, as we define now this, the last thing is to define the theme here, which I like to call always theme for the win. So this I like to turn into a function, and then within this function I like to define several things. So the first thing I like to define within this function is I want to make my theme devoid of any extra elements. So that's why I'm using this theme void. And then for defining specific things within this theme, I then like to call this theme itself. Now, the first thing I want to here define is the legend position. So for the legend position, I'm just going to put legend on the right hand side. You can also choose some other sides. It can also be, for example, as you can see here, left, right, bottom, top, inside, or none. So no position at all. But I do think with the specific temperature anomaly map, you do want to have also the legend here. All right, then we can also specify some other things related to the legend. So for example, we can specify the legend title. But a very important thing here is to declare that this is text, so that ggplot2 also knows that. Now for the size, I'm going here with the base font. So I'm just going to go here for the size 20. And then for the color, I'm probably going to take something like, I don't know, let's say gray 20. So that would be a bit kind of a darker gray. Okay, and then what else can I choose here? I'm wondering, I mean, I could also align legend title in a specific way, but I think I'm fine here with this one. All right, then I can also, what I did for the legend title here, I can also do for the legend text. So I just need to change things here. I'm going to keep the same one. I'm just going to go for 15. So I'm taking here a bit larger pixel size so that we can clearly see what's going on. Now I also want to have a plot here. So I'm definitely going to use plot title. So I'm just going to copy this one and paste it here. And then instead of legend title, I'm just going to write here plot title. And then for the size, I'm going to be using a much larger one. Let's say, for example, 30. For the color, I might be using a bit, a bit lighter gray here. And I do also want to horizontally justify. So I want my title to be in the middle of the plot. For this purpose, I'll be using 0.5 here. If you want to move it more towards the right, you need to use the value of 1. And if you want to move it towards the left, you need to use the value of 0. So 0.5 comes as a natural middle ground, of course. One more thing, I want to move the title a bit closer to the map itself. So I'm going to be using here a bit of a negative values for this vertical justification of it. All right, and now once we have this, what will be also very cool is that we add a caption also. So in the caption, we can indicate what is the source, of course, of this map, what is the data source. So here I'm just going to change here for plots, instead of plot title, I'm going to put here plot caption. And then, of course, I'm going to readjust here so we don't need 30 pixel size. We can go for 10 maybe, or we can also keep this, for example, horizontal justification 0.1. And then the final step is to basically make everything around your plot shrink in space. So you want to actually decrease the white space around your map, and for that I'm using here plot margin. All right, so for the plot margin, what we can do is for the top hand side we can declare it to be 0. For the bottom hand side, we can also declare it 0. For the left hand side, also 0. So this means we are neither expanding nor contracting. So we're just kind of getting rid of this extra space. But because on the right hand side, we do have our legend, I am going to assign it a bit more space. So I'm going to expand it on the right hand side. And then finally here, you just need to define what are the units of your measure. Okay, let's write a code that will create finally the map for us. And I'm going to call this map 1. Then I'm going to call here ggplots2. And then, as we said before, I'm going to be using here tidyterra because it allows me to plot a raster file without turning it into a data frame. So from this one, we can use geomspat raster. And then over here, we simply need to declare that our data is this temp anomaly April 2024 proj. That's all. So that's the first layer that we have. Now the second layer that I want to add here is the SF layer. So over here, I want to add this world shapefile. So I'm going to be adding here world underscore SF and then proj. That's one. The second one is we need to define what is going to be the color of the boundaries, so national boundaries. So over here, I'm going to go probably with this charcoal gray. And then we can also define here what is going to be the line width here. Now, of course, this is depending on your, version of ggplot2. It might be size, it might be line width. So for the line width, for example, we can go 4.5. And then here for the fill, I would like it to be transparent because otherwise, if I don't define it here as a transparent, I'm not going to see the values for the temperature. Okay, and then we can add finally the third layer, which is again the SF object, but this time we are talking here about the ellipsoid. So for the ellipsoid, we can go for the same color, but the line width could be, I think, a bit smaller. So let's say 0.15. And then again, this also needs to be transparent. All right, now that we have this, we actually have two options. We can either use this to map continuous values or we can use bin values. So now in most of these temperature maps, they use bin values. So now I will show you in this tutorial how you can use color space and one of its functions to actually create a map with binned values. All right, so color space has a function which is called scale and then fill bin divergent x. That's the name of it. So over here, it's kind of a pretty much the same as scale fill gradient or scale fill continuous. So we can start off by first of all defining what is going to be the legend name. So we can put here, for example, Celsius degrees so that we just know. Then we can also define here the palette. So the palette is those temps. So that's actually the advantage of this one, because we don't need to define the colors. The colors that I defined previously can be used for the continuous scale, and I'm also going to show you how we can map using that one. All right, then over here what you can do also is you can define the color for the NI values. I'm going to go for the white color here. Okay, and then once we define this, we can also define the middle. So middle for us can be 0. I think that makes sense. So that means there is no change in the temperature if we compare April 2024 to the baseline. And then finally, we can also here define the breaks. So those are the pretty breaks that we already created. All right, and then once this is done, what you can do is go ahead and customize a bit the legend. This is achieved using guides argument. Now over here, what you need to do is you need to define your main aesthetics. So our main aesthetic is fill. And because we have here continuous measure of temperature anomaly, we need to define this as guide color bar. And then for the direction here, I would like it to be vertical. So I can also define it here, vertical. You can also choose to be horizontal. And then also you can a bit manipulate here the bar height and the bar width. So for the bar height and bar width, we are talking here about units. Let's say, for example, because it is vertical, I want to give a bit more space. I can go, for example, for, let's say, 60 millimeters. So I can define here 60 millimeters. And then for the bar width, I can define something that is much smaller because I would like the bar to be also thinner. So let's say, for example, I can go here for 3 millimeters. Of course, guides is a very, very cool argument because you can also define some things as, for example, what is going to be for example, the title position of the title on my plot. So I can, for example, say here it's going to be top. Then I can also define, for example, one is going to be the label position. So positions of the legend labels. So we can use here, for example, bottom. You can also, for example, well, in this case, not really bottom because it's a vertical. Maybe it would make sense to be left or right. Let's say, for example, it can be left. You can also define some other things, for example, here, because our labels are on the left-hand side. Maybe we can, justify them to the left-hand side a bit. So if the labels are, on the left, yes, exactly. So we can do that. We can also make the title to be in the middle. So for example, we can use title adjust for that. So we can put 0.5. And there are also some other things that you can do. One thing that I think it's very important if you're using here a vertical legend is to turn off this by row so that those legend keys are really put next to each other. All right. And once you actually do this, once you define the guides, one of the last things is to define the labs here. So for example, for the title, what we can do here is we can, for example, say, okay, what we are showing here is actually temperature anomaly for April 2024. And then you can, for example, you can also write here baseline 19, for example, baseline or versus average for 1950, 1980. And then what also would be really, really good is that you can also add, for example, the data source that you're using here. So you can, for example, go ahead here. And since we already defined the caption, you can just go ahead and say here data, land ocean temperature. This one, you can also maybe add NASA here. And you can also add, for example, GISS. All right, and then once this is done, then you can call, of course, the theme for the wind that you previously defined. And finally, you can see the map of temperature anomaly for April 2024 versus the baseline for 1950 to 1980. Warmer colors indicate that the temperature for April 2024 is higher than the baseline, and colder colors indicate that the temperature is lower compared to the baseline. Now, what you can also see, and what is the advantage of bin breaks, is the simplicity. So here you can see that the bin scales group values into intervals, and this makes the map easier to interpret. So there is clearly a color contrast between different anomaly groups. Now, the problem with the bin breaks is the loss of precision. So by doing this grouping, we are sacrificing precision by grouping values. So we are kind of introducing here our own bias by plotting certain groups. What I'm going to show you in the next step is how you create a different type using continuous breaks, which the main advantage of this one is it allows for a more precise representation of values, and because anomalies are smoothly interpolated between breaks. Okay, in this part I'm going to show you how you can also create continuous breaks and then the map based on continuous values. All right, so first of all, we're going to just comment out this one. And then from base ggplot2, we'll be using scale fill gradient 2. Now, the advantage of this one is that you can define your own colors for the lowest, highest, and the mid values. Now, the first thing we'll grab from the previous one is the legend title name. That's the first. And then for the low values, so those are the temperature values that are colder compared to the base average, we'll simply using this light blue color from the temps palette. So we're not going away from that palette. Second, we're going to be defining here mid. So for the mid, we're going to be going for something which is like a very, very light yellow, almost white. And then finally, for the high values, which means the temperature that are higher than the baseline, will be going again for the pink value from our temps color palette. Now, one more thing here is that you can also define your midpoint, and it's called midpoint instead of just mid because you already have the argument mid here. So for the midpoint, again, we'll be using 0. And then the rest is pretty much similar to the standard, scale fill gradient. One thing is you can define here the breaks. We will also want to probably define here the labels. And labels will be actually the rounded breaks, meaning we don't want any decimal places after this breaks. And the final one is also going to be like in the previous what we did, and that is defining the color for the NA values. In this case, it's going to be white, and just adding here plus so that we add the code. So once we run this, you will see now a bit different map. And the difference in this map is that we now have a map with a smooth gradient of temperature anomaly. So we don't anymore have these anomaly groups that are clearly visible. So the advantage of this is that it allows for a precise representation of anomaly values. And of course, for the smooth transitions, because anomalies are really smoothly interpolated between these breaks. Now, one thing that is kind of a disadvantage compared to the bin ones is that there are too many breaks here that can clutter the map. I know we have the same amount of breaks in like the legend itself, but when it comes to kind of finding these different patterns and what they actually mean, and then linking them to the legend, that comes at a cost, I would say. And then there is also the visual perception here, which is even though this continuous scale offers precision, our eyes are struggling a bit to accurately judge, what is the intensity of these different hues. One thing you will notice here is that exactly the colors are much actually weaker compared to the bint map. That was a really fun experience, but sometimes you might want to calculate and visualize temperature anomalies for the entire year. And this is exactly what I'm going to show you next. We're going to be computing and then visualizing the temperature anomalies for 2023 or the entire globe. So the first thing we need to do here is actually we need to average the temperatures for all the 12 months or 2023. So that means that first of all, we do need to create a mean or an average for these values. So how are we going to do this grouping and then aggregation? Well, first of all, let's work off our main file, temp anomaly. And then what we need to do next is use again subset function from Terra. Now this time we want the data between January and December, and this is how we do it. So again, we use the time here, and then we use the time from temp anomaly, of course. And then what we want to do here is we want to say we want months that are equal to or higher than January. So that means that we need a date which is 2023 in this case, so 2023, 01, and then 15. Remember, 15 is used as the first date or as a signifier of day of the month here. So 15, not 01, but 15. All right, that's the first thing. And then our second condition, putting here and, will be that we want also the months that are preceding December. So that means here, smaller than or equals to the date, which is December 15th of December 2023. All right, so once we actually have this, one last thing to do is we need to calculate the average. So how do we do that? We probably know how to do it with data frames, but how we do this using just a raster using Terra. So Terra has another fascinating function here, which is called app, which allows you to just in one line, aggregate this group and then calculate whatever you need. So in this case, we need actually mean. So we simply specify here mean. All right, and then as you actually run this, you can then see what actually this means. You can simply inspect here. So you can see that the mean here is -0.6 Celsius and the maximum is 4.4, almost 4.5 Celsius. All right, so once we actually have this, the next step is to reproject this temperature anomaly raster file for 2023 into this Robinson projection. So we are simply going to work here off this one, just added proj to it, and then we're going to use once more project function from Terra, and we'll be passing, of course, this newly created one. So temp anomaly 2023. And okay, and once we have that, we simply need to say what is the projection here. Well, the projection is this Robinson proj. And then just to kind of shorten the number of lines we have here, we can immediately go ahead and then also crop this using, of course, the ellipsoid, which we previously turned into this Robinson projection. Now for mapping, we're going to use simply the same steps as before. So we might just simply copy some of these. So we need breaks, we need colors. We're going to stick to the same theme as well as the palettes, so we can simply put them here. So the breaks are going to be this time based on this one, so temp anomaly 2023 proj. And then length is going to be based on this one. So we have these, and then theme is the same. So in terms of the map itself, here it's really depends on your preferences, whether you want to create a bins or you want to create a map with continuous breaks. So for example, let's say we're going to go for the bin here. So I'm just going to comment this one out and use the one for this. So over here, I'm just going to call this object, let's say map2. And then we do here need to replace some of the things. We're going to be using different raster. So this one for 2023, we're keeping the world's shapefile. We're also keeping the ellipsoid for the globe. We're of course going to be using this one. So this one stays. And one thing that we want to change here is simply we're going to have here a temperature anomaly for 2023. And the temperature anomaly map for 2023 clearly shows that the anomalies are much higher across the globe for this period. And for the end, I want to show you something special. That is how you can also create temperature maps with orthographic projection. Orthographic projection basically turns your 2D map into a 3D map, giving it a perspective. So how do we do this? Well, first of all, we define here the orthographic projection. And then over here, what you want to do is you want to put the latitude and longitude for your point, which is going to serve as a focus of the map, meaning that part is going to be revealed on the map itself. So for this specific one, we're going to be having the map, which includes the vision of Europe, Africa, and also Asia. But if you actually change this latitude and longitude for the ones of your, let's say, favorite place or a city, you will have a different one. And that's the beauty of orthographic maps. Now, how do we actually transform this? Well, for the raster file, it's pretty easy. So for the raster file, what we can do is we can use the one for April. So temp anomaly 2020, or actually temp anomaly, and then April 2024. And then we can simply call it ortho, and then we can use Terra and then project. And then within this one, we wanna, of course, transform this main one. And then simply here, we pass this ortho proj. Now this is for the raster file, that's very straightforward, as I said. But for the shape files, it's a bit tricky. So I'm gonna show you now how you can also transform your world shapefile as well. We're gonna create here world SF ortho, and then we're gonna be working based on this main world shapefile. So now the first thing, of course, is to transform. That's pretty easy parts because we just need to use st transform from the SF package, and then we need to transform into this ortho projection. So that's the first part. Now, once you actually transform this, what's going to happen is that some of the polygons that you have, or in our case lines, they're not anymore going to be interconnected. So there are going to be some features that are not going to have at least four points. You need 4 points or 4 vertices to create a certain enclosed shape. So what we're going to do here is, first of all, we're going to create a field which is going to tell us how many points we have, and then we're going to remove those features that have fewer than 4 points. So we're going to go ahead and use dplyr from tidyverse, and then we're going to create here object called numPoints. And then over here, we need to include a package which is called mapView. So we didn't include it at the very beginning. So if you don't have the mapView package, simply, you need to simply install it here. And then what we need to do is we need to call mapView, and from mapView npts. So this one is going to count the number of points for each feature. So what is the feature here? The feature is geometry field from our shapefile. And then what we want to do is we also want to calculate this by feature. So we're going to turn on this option, which is so count the total number of vertices false, off, or for each feature, which is true. All right. And then once we do this, the very last step is to, as I said, filter those which don't have 4 or more vertices. So what we need to do here is simply say num points, those that only take those that are equal to 4 or higher. All right, and now if we want to just visualize, we can simply go back to the part where we created a map of temperature anomaly for April, and we can just simply copy this whole chunk. Then we can actually go back down here and we can simply paste this. So now it's all about customizing our map and of course adding these new objects that we have, and maybe get rid of some other objects, such as, for example, the ellipsoid part, which we don't need basically because we are now turning this into a 3D object. So first things first, let's actually put here this one here, the ortho one, and then what else do we need here? Of course, we need also the this world SF one, ortho. So that one actually comes here. As I said, we're not going to be using ellipsoid, so I'm just going to comment it out here. We can again use the bins, so I'm actually going to enable this one, and that means I need to comment out the one which provides us with the continuous legend break. All right, and we can then check in the entire code if we're actually ready. We can name also this map 3. And in this final map, you can see how we shifted the perspective and turned the 2D effectively into a 3D map of temperature anomaly for April 2024. So this is another idea for you how you can also present your maps. Again, you can also change the focus of this map. So it doesn't need to be focused on Europe, Asia, and Africa. It can also be shifted to, for example, Americas or Australia or even the poles, depending on your preferences. And that's all for today, folks. In today's tutorial, you learned how to create effective temperature anomaly maps for the entire globe using both the Robinson and the orthographic projections. If you would like to replicate today's maps, I prepared the link to the GitHub repo in the description box below, so do check it out. Feel free to clone it, reuse it, modify it as you see fit. If you have any questions, comments, or just general feedback, feel free to reach out to me here on YouTube, but also on Instagram and X. If you're new to R and you seek to expand your data visualization and geospatial knowledge with R, I prepared a few cool tutorials for you, so do check them out. See you next time.